Welcome to the Deep Dive. We're the place that takes complex research and, well, makes sense of it for you. Today, we're tackling maybe the biggest cosmic mystery out there, dark matter. Just think about this for a second, Everything we can see, all the stars, the planets, the gas, that's only about 5% of the universe. The rest, well, a huge chunk, something like 27%, is thought to be this invisible stuff, dark matter. It's the gravitational backbone holding galaxies together, keeping them from just flying apart. It's cosmic glue, essentially.
Exactly, invisible glue. And finding it, that's the challenge.
Yeah, it's like trying to hear the quietest whisper in the middle of a rock concert. Our usual sensors just aren't sensitive enough.
They get swamped by noise. The signals we think dark matter might produce are predicted to be incredibly faint.
So our mission today is to really dig into a fascinating new approach from researchers at Tohoku University. They're not just trying to build a bigger sensor, they're proposing something smarter, a whole quantum network.
A network designed specifically to boost sensitivity way beyond what we can do now. It's a really different way of thinking about detection.
And it leverages tech from a field that's already booming, right? Quantum computing.
That's the really clever part.
Yeah.
They're adapting superconducting qubits, these tiny circuits that have to be kept incredibly cold, the same things used in quantum computers. But instead of computing, they're using them to sense the environment with extreme precision. Okay, let's unpack this properly, because you really need to appreciate just how difficult this problem is. Dark matter. Well, if it interacts with normal matter at all, it does so very weakly. Maybe only through gravity, maybe some other force we haven't found yet.
So the signal, if there is one, is absolutely minuscule, buried.
Completely buried under noise with traditional methods, which is why we need to turn to quantum mechanics.
Right. Quantum sensors operate under different rules, allowing them to pick up things classical sensors would just miss entirely.
Correct. But the Tohoku team's insight wasn't just about using one super-sensitive quantum sensor.
It was about linking them together. Quantity and, crucially, organization.
Precisely. It's this idea from quantum metrology. You connect multiple smaller sensors, these qubits, and you entangle them or coordinate them in specific ways.
Okay. So they work together. The source material had this great analogy.
The coordinated team one.
Yes. Much like a coordinated team achieving more together than any one member could individually. That really clicked for me.
It's a good way to put it. The network as a whole becomes far more sensitive than just adding up the individual sensor capabilities. It's a collective quantum effect.
But engineering that coordinated team, that sounds complicated. How do you actually build and structure that network of qubits?
Well, that's where the geometry comes in. It's not just that you connect them, but how. The pattern, the structure of the network, the graph, as they call it, makes a huge difference to performance.
So they needed to figure out the best way to arrange the team, essentially.
Exactly. They started with manageable systems, testing networks of 4 qubits and then 9 qubits, and they looked at different ways to wire them up.
What kind of patterns did they test?
They looked at some standard network topologies. There was the line graph qubits, connected one after another like beads on a string.
Okay, simple as.
Then the ring graph, where you connect the ends of the line, making a loop.
Right.
Also the star graph. Imagine one central qubit with all the others connected directly to it, like spokes on a wheel.
Okay, so information flows to the center.
And then there's the kind of ultimate connection pattern, the fully connected graph.
Where every qubit is linked directly to every other qubit.
That's the one. It allows for maximum information sharing, maximum entanglement across the whole network. No bottlenecks.
So intuitively, you'd think the fully connected one must be the best, right? Just connect everything to everything.
Well, theoretically, yes.
Yeah.
It often gives the highest potential sensitivity. But it's also the most complex to actually build and control, especially as you add more qubits.
The practicalities.
Always the practicalities. And what the research showed was really interesting. Even simpler structures, when optimized correctly, gave significant sensitivity boosts. Dr. Labinho, one of the researchers, pointed out that, quote, the network structure plays a key role, and we've shown it can be done using relatively simple circuits.
So clever design can sometimes beat brute force complexity. That's a really important finding.
It is. It makes the whole approach seem much more achievable.
Okay, so they've designed the physical network structure, but how do they actually tune it to listen for these faint dark matter signals? And critically, how do they filter out all the background noise?
Right. 2 key steps there. First, tuning the network. For that, they use something called Variational Quantum Metrology, or VQM.
VQM. Okay, what does that do?
It's essentially a way to prepare the best possible initial quantum state
Yeah.
for the measurement you want to make. You need the qubits to be in a very specific, highly sensitive entangled state before they even start listening.
How do they find that state?
VQM uses a feedback loop. It runs measurements, sees how well the network performed, and then uses an algorithm to tweak the preparation process for the next run. It iteratively learns the optimal setup.
So it's a bit like training a machine learning model. But here, you're training the quantum system itself to be maximally receptive to that tiny signal.
That's a great analogy. Exactly. You're optimizing its listening state. But even with the perfect state, you still have noise. The universe is messy.
Yeah, cosmic rays, heat, stray electromagnetic fields, it's got to be everywhere.
It is. So you need a way to reliably pull the signal out of that mess. And that's where the second tool comes in, Bayesian estimation.
Okay, Bayesian estimation. I've heard of that in statistics. How does it apply here?
It's a powerful statistical method for dealing with uncertainty. As the data comes in from the qubit network noisy data, remember Bayesian estimation constantly updates the probability of detecting a real signal versus just noise.
So it's not just averaging or simple filtering. It's like
Yeah,
continuously reassessing the evidence.
precisely. It's like sharpening a blurry image, but in a statistically rigorous way. It lets you quantify your confidence in the result even when the signal is incredibly faint compared to the background.
So VQM primes the system, Bayesian estimation cleans up the results.
That's the workflow. And the really exciting part,
What was the key result?
they found that these optimized networks consistently beat traditional methods, meaning single quantum sensors not linked in these optimized ways.
Even with noise.
Yes. Crucially, the advantage held up even when they simulated realistic environmental noise. That's huge. It means this isn't just a theoretical idea for perfect, noiseless quantum computers of the future.
It suggests this approach could actually work with the quantum devices we have or are building right now.
Exactly. That's the potential breakthrough here for experiments like dark matter searches.
Okay, so the big prize is potentially finding dark matter, solving that huge cosmic puzzle. But whenever you make such a big leap in measurement precision, well, other applications usually follow, right?
Oh, absolutely. If you can measure things this sensitively, it opens up possibilities across many, many fields.
So what else could this kind of quantum network sensing be used for, beyond looking for dark matter?
Well, the researchers mentioned quite a few. Think about quantum radar, potentially much more sensitive radar systems, or improving gravitational wave detection.
We're already detecting black hole mergers, but this could make those detectors like LIGO and Virgo even more sensitive.
Potentially, yes. See fainter signals or signals from further away, maybe even different types of gravitational wave sources from the very early universe.
Wow. What about more down-to-earth stuff?
Ultra-precise timekeeping is a big one. Atomic clocks are already amazing, but networked quantum sensors could push their stability and accuracy even further.
And better clocks mean better navigation, like GPS.
Exactly. GPS relies on incredibly precise timing signals from satellites. Improve the clocks, improve the timing, and you could potentially get GPS accuracy down from meters to, well, much less, maybe centimeters in some applications.
That would be transformative for things like autonomous vehicles.
Definitely. And think about medical imaging. MRI machines work by detecting subtle magnetic signals from inside the body.
Could these networks make MRI scans sharper, see smaller details?
That's the hope. More sensitivity could mean higher resolution images or detecting biochemical markers of disease much earlier. It's about seeing things you currently can't.
And you could even use it for geology, maybe. Finding things underground?
Yes, detecting tiny variations in gravity to map out underground structures, water resources, mineral deposits, hidden tunnels even. This kind of network sensor could act like a huge distributed gravimeter with incredible sensitivity.
It really drives home that sensitivity is key across so many areas.
It really is. The lead author summed it up well, saying this research shows that carefully designed quantum networks can push the boundaries of what is possible in precision measurement. And importantly, it opens the door to using quantum sensors not just in laboratories, but in real-world tools.
So it's about moving quantum sensing out of the lab and into practical technology.
That's the trajectory, making quantum advantage a reality for sensing applications.
Okay, let's recap this deep dive then. We started with this enormous mystery, 27% of the universe missing, this dark matter. And the proposed solution wasn't just a bigger detector, but a smarter one. linking quantum sensors, these superconducting qubits, into optimized networks.
Using specific graph structures, lines, rings, stars, fully connected and finding the best geometry.
And then tuning those networks using sophisticated techniques like VQM,
To prepare the optimal quantum state.
and using Bayesian estimation to filter out the noise and build confidence in the result.
And the result is a system potentially sensitive enough to finally detect dark matter, but also applicable to a whole range of other technologies needing extreme precision.
And the team isn't stopping there, right? What's next for them?
They're planning to scale up, explore larger networks, more qubits, and also work on making these sensors even more resistant to noise. That's key for real-world deployment outside controlled lab settings.
Makes sense. You need robustness if it's going to work in, say, a hospital MRI or a field geological survey.
Absolutely.
Okay, that brings us to our final thought for you, the listener, to take away from all this. If simply changing the structure, the organization of how we connect these quantum detectors can give us such a massive boost in our ability to measure reality, what does that imply? Could it be that some of the fundamental limits we think exist in physics, limits on what we can know or detect, aren't truly fundamental barriers, but rather limitations in how we've organized our measurement tools?
If we get better at building the team, how much further could we see? What other whispers of the universe might we finally be able to hear?
Something to think about. That's all for this deep dive. Thanks for joining us.